Hello folks, yeah, welcome back to BFI 12 or Management 313. Folks, here in my lecture, this lecture I'll be talking about the shortest route problem, and then as I discussed in my introduction, so many of us do plan our trips from point A to point B, and we look at either the Atlas or go to the MapQuest to find out what is the shortest in terms of the time or the distance to take us from point A to point B, and this is such an application over here. Okay, I am looking at a problem 613 on page 214 in your book, or in the problem data set that I have uploaded on the blackboard. Now in this problem, this Seattle to London, so these are various different airways or the air routes that a flight can take, and based on the weather conditions and all, so you might have to suggest to them what's the best route to take. Okay, now here I want to kind of make a distinction between two sets of problems that can arise here, and one is we have this information beforehand, that is, so this is the amount of time it takes from Seattle to 3 different locations. Let's say this could be the points on the route. Okay, it need not be the airports, but this could be the points on the route A, B, and C, 4.6 hours or 4.7 hours or 4.2 hours. Likewise, some other intermediate locations are nodes and the final destination London. Okay, now given the information beforehand, as of right now, if this is the number of hours that it takes, what is the shortest route possible between Seattle and London? And this could be the information based on the current weather conditions. Okay, now on the other hand, okay, now that's the kind of problem that we are going to solve. Once we know the information about the weather, how long it takes, that information remains constant. Okay, so we want to solve this problem in a static condition. Okay, that's what we will be doing here. Another variant of this problem is we left Seattle, and based on the current conditions, we are en route. Then let's say that we are somewhere over here, point A, then we get the updated information that is there is a major weather disruption, and based on that, what is the best way to go from A to London, whether to go to D or London, or to go to E or to London. Okay, so that is called, those kind of problems can be solved. They are called dynamic programming. Of course, we will not be addressing those kind of problems here. Maybe in an advanced class, we could talk about dynamic programming. Given that I am here, what is the best way for me to go from this point onwards, not from the origination point, but from this point onwards. Okay, now in this problem, so we have these distances in terms of the hours that it takes from between each node is given to us here. Now we have to solve this problem. As before, get from to Seattle to point A, B, C. From point A, you can go to either D or E, and likewise get all those paths, the connecting pathways over there. Then, as I said before, I have defined the range names there, and that is from, and that is the route, the decision variable to there, and you see the 613, 613, 613 next to that, because what I had done earlier was, I wanted to bring it to your attention, was I had a workbook in which I had each separate problems on separate worksheets. So, but when I was defining these range names, I was trying to use a common range name like from to solve the other problems, but I was getting into trouble. So that's why I had to go back, and then I had to redefine the range names and add the problem number to that to overcome that a problem that I was facing. Now here, from Seattle to A, list down the miles, basically all hours it takes to travel from point Seattle to that, from 2 destinations over there. That's a decision variable, and total hours is nothing but the route that will take times the corresponding distance. That's a sum product. Okay, but now you got to look at it. Now here the decision variable, there is only one route, meaning that there is just one route that is going to leave from Seattle and reach London. So the decisions that you will see here are 0 or 1. meaning that 0 means that route was not taken, 1 means that segment of the route was taken between those two nodes. Okay, so that's what we have here. So the net flow again is nothing but, as I said before, the command is look into the list from, in that list, look at the node that is there, F7, that is there. So go and locate this node from this list and go and then pick up the corresponding, the entries in this cell. That is one. The other part is, again, look at the node that is in question. Now look into the 2 column and locate that node, go to the corresponding cell under the route column and get that. Okay, so that's the net flow. So the net flow is from Seattle, there is one route that's going to be taken. That is, now since we adopted going out as positive, that's one route is going to go. Then intermediate points, if it comes in here, it is going to leave. So the net flow is 0. What comes in should leave. So the net flow is 0. If it doesn't come in, it's not going to leave. So 0 minus 0 is 0. So that is, those are the zeros. So at London, so one flight is going to land, or the route is going to come to an end. So this is the receiving part, so that's that -1. So you have this, and again, whenever you copy and command, go back and check to see the net flow are there. Okay, then once you have that, go to the data solver. Now what we want to do is we want to minimize my total hours taken to travel from Seattle to London. So minimize that, subject to the constraint route. You can just type route or go and then pick up the cells. Add the constraints. That constraint is the net flow should equal to the right side. Click OK. Options, linear model. Click OK and solve. Found a solution. All conditions are satisfied. Now here it takes about 11.3 hours to reach from Seattle to London, and the route that is taken is, zeros are the ones that you'll not be taking. From Seattle you'll go to node C, that is that node C, and from node C you go to E, that is that E, and from E you go to London, and that's those 3 ones is that what you see. S, C, E, L, N, that's the route that you will take. So one flight left and one flight, the same flight reach London. So this is the shortest route problem.